Okay, good afternoon, everyone. So today we welcome Simon S.Vorhammer. We are very excited to meet him, finally, I would say.
Hi.
So Simon is a computational designer, architect, working at the intersection of this computational design, material science, doing some, he has worked at Foster, Arma, Lava, like some very important offices in the industry. And he studied at Technical University of Munich, also at ETSAM Madrid. So I think that he's very close to us also culturally in a way. And I think that you're gonna enjoy this lecture. So thank you so much for accepting the invitation, Simon.
Yeah, thank you for having me. Thank you very much. It's a great honor for me to be here actually, looking at the people who were here before. This is a big honor. So, as Gerard said, I'm a can you hear me well? Is it too loud? Okay. So, as you said, I'm a computational designer, and I often get asked what I do as a computational designer by architects or non-architects, and I usually go with an answer that goes something like, well, I use computers to come up with systems containing dependencies and rules to control or generate, create, handle complex geometries, mostly complex geometries. And then I usually take the example of the Allianz. Sorry, this stopped working. The football stadium in Munich, made by Herzog de Meuron, although I haven't worked on it, but people know it and they understand why it is tricky to draw 1,800 cushions, which all vary in size and geometry just slightly. So it makes a lot of sense to use an algorithm there. But then over the course of the last, well, say 15 years, I found myself working on a variety of projects that don't fall into that same exact category. And while I was preparing for this talk, I collected a couple of projects that I've been working on, and I thought about what could be interesting to you. And well, so I didn't want to focus on one specific project, but rather talk about that journey, if you will, that computational journey that led me into very different directions. And I was also thinking about a system of how these projects could be categorized. So what I mean by that is, if we look at the first column, one thing I'd like to mention is this is not a comprehensive list. Of course, there are other areas. It's just what properties would fit to the projects I was involved with. So if we look at the left column here, I thought about what can we do as computational designers, on a basic level. And I think, of course, there's classic computational design, where, for example, as architects working in a big architect's office, working on competitions, caring about the design, the shapes, but not caring too much about how things get built. And then there's the other side, well, I call it design to production, where you take existing designs and make it work. Like design to production, there's even a company which is called like that, which I'm sure you know. And then there is DFMA, design for manufacture and assembly, which I think is, well, in my definition, is when you do both. Like when you don't even have to follow through all the way, but I think if you know how things will get built in the end, then it's this approach, which is integrates all aspects. And then you can also work on the processes themselves, make tools, work on workflows, making tools for yourself, making tools for others. And then also, because computational design is not a profession, right? Or at least in Germany, I think it's the same in Spain. I feel like I feel like a free radical, like a chameleon that can attach to other professions, be so we can wear different hats. We can wear the hat of an architect. We can even wear the hat of a consultant. a contractor or a manufacturer, right? We're not bound to one certain profession. And then there's building, like project types. We can work on buildings, interiors, installations, products. And then there's a fourth category, which is it configurable or not, the project. I will get to that, and I'll explain what I mean. But first things first, I want to show you 3 projects that can be grouped as I was working as a computational designer, not knowing how to build this. As an architect, it's a building, it's not configurable. This was like a uni project, a tower, a concept for a tower in Munich, with a complex, like geometrically complex facade. I would have needed Grasshopper desperately, but it didn't exist at the time. In fact, it was called Explicit History back then. Maybe some of you know, but I didn't know how to use that. So I was lucky that my professor liked it. I had modeled this for like 2 days in Rhino. My professor liked it, so I didn't have to change it, but I was very lucky. After an internship at Foster & Partners in London, I saw like the special modeling group. They are these experts. At the time they were working with microstation, generative components mainly, and well, I didn't work with them, but I got the bug. I went back to Munich and started deep diving into parametric design. At the time, this was very different. There was no formal, there's no education for being a parametric designer back at the time. Like Grasshopper was all new. Like you could go through the Grasshopper primer and then go to the Grasshopper forum, but that's it. What I learned there, or what struck me was that my expectations on parametric design were actually quite different than what it actually was, I think. I had expected it to be this magic black box where you input something, or you have like these nice buttons that you press and you get something back, like a nice result. And if you're not happy with the result, is this cutting out a little bit? Or is it, you can hear me? Yeah. So I was expecting it to work in the way that I think generative AI is used by most of the people right now. You come up with a prompt, you send that prompt to the black box, you get something back. If you're not happy, you change the prompt, but you never understand the black box. And I think the fundamental difference with parametric design is that you are actually, in fact, working on that black box. You're defining that black box. So the third project, which falls into that same category, me working with the architecture hat on a building that is not configurable, was this pavilion for Samsung. I was working at a company called Chail in Munich. Not Chail like prison, but C-H-E-I-L. And I was like the one-eyed among the blind, meaning that I had like 1 or 2 years of Grasshopper experience and everyone else did not have that. So that gave me the opportunity to work on the design of that building. So on the right-hand side you can see the finished building. On the left-hand side you can see our a render and the model. And what was remarkable about the process was that we completed stage 3, scheme design, and sent it over to the contractor in South Korea. And then we basically never heard back. We actually thought it's not getting built. But I think 6 months later we saw images from the construction site, and from what we heard, we heard that a team of 20 people basically redrew everything that we had based on our renderings. So we had expected it to be like a dialogue, like with this parametric model. We expected them to come back at us and want changes or stuff, but none of that. And I thought to myself, there has to be a better way. I want to be involved in the entire process if possible, even if that means that the projects are smaller. So in 2013, I went to Sydney in Australia together with my partner, now wife, to work for Arma. The founder, Robert Beeson, actually did an internship at Design to Production in Zurich, like a long time ago, and then he went back to Australia to actually do the same thing, right? So take designs of architects that has complex geometry to it and make it work for the contractor who have to build it. So this is like a typical project. It's a private residency near Melbourne, in Toorak, and we took care of modeling and outputting fabrication data for the underside of that zinc shingle-clad bowl-shaped roof. So we didn't produce any plans except those drawings that you see on the left-hand side, but this was more for contractual reason and for spot checking what had been cut is right. So there was like one of the principles with working there was that we tried to produce as few plans as possible. Like just model everything, have like a very comprehensive 3D model and draw no plans if possible. Another project which was kind of typical for Arma was this ceiling in the central business district of Sydney for the HSBC bank. And well, same type of project. The design was by FJMT, and we were working for the facade contractor. And what was a little bit special about this one was, well, here you can see, like we this is on the left hand side. You have a screenshot of the 3D model that we developed. And one thing that is worthwhile mentioning is that we had to wait for the steel contractor to finish the steel trusses before the cladding could be produced, because we did not know how precise this was going to be. In fact, it was like it was deviating by up to 20 centimeters because it was sagging as a whole. So we developed like a parametric model for, let's say, I think it was 3 months. We were working that based on the 3D model of the steel contractor. And then once it was up, it got scanned, and we could just swap the 3D model for the scan of the reality of the real steel, and that way we didn't lose any time. And I think so then all the fabrication data could basically be re-output within a matter of like hours. And that to me is one of the biggest advantages, apart from working parametrically. That one obviously is you can change things, you can change parameters, but also you can break away from that linear planning process. You can work on topology in parallel to other stuff and care for the precise inputs at a later stage, as opposed to working on waiting on every bit of information until it's complete before you start. So I wanted to mention, because I mentioned like being the one-eyed among the blinds. At Arma, I was the one-eyed among the two-eyed, so to say, which I think is also a good position. If you're working in an office and you have like you know your stuff, but there is people who know much better, but you still know enough that you get like projects. They let you handle projects, and this is a very good position to learn a lot. So I think during the 2.5 years at Arma, I learned like most of what I know about Rhino, Grasshopper, and construction. So this is a third project, which is the same category. This time we're working for the steel contractor. It's the Optus Stadium in Western Australia. We were responsible to model the east awning, which is like a 100-meter long roof consisting of many different parts and assemblies, all very similar, but then in the end they're not the same. Same thing, like a parametric model, but this time for the steel contractors we had to output shop drawings. And what you see here is like all the shop drawings that we produced, and like we spent a lot of time automating these shop drawings, and we like had to learn that like automating drawing is drawings is so much harder than outputting fabrication data, CNC data. Like that's like another good reason to for me to try to avoid plans as much as possible, right? Amma did also this project, which is a bit different than the other ones, because here they were responsible for basically everything. They did the design, they won a competition. This is a pavilion for a art gallery in the heart of Sydney in Surrey Hills. It's a pavilion consisting of an outer shell made from thermally deformed 5-axis cut Korean elements held together by an intermediate layer of stainless steel spigots, we call it, like connectors, and an internal skin of singly curved 1 millimeter thick steel sheets. So as I said, with this project we did basically everything, do the design, be in the factory, manufacturing everything, installing it, and then in the end we disassembled it. So this is, to me, so now the responsibility here changes to DFMA for the first time, and that was like a revelation to me, because it's it lets you do two things. You can take very informed decisions at an early stage if you know already how you are gonna build it in the end, and you can learn a lot from your own mistakes. Like, right, so as I think you mentioned it earlier, it's like you have this playground out there and you do all the experiments and you can leave it there and you learn so much from, I don't know. This is perfect. I really said, okay, ideally I want to work on projects like these where I follow through with the entire process. But I also must admit that this is easier for smaller projects, for pavilions, which is not like a it's not a whole building with a facade, and it's not a weather hull, and you know it doesn't involve like many different contractors. So it's easier for smaller projects, but you can transfer that principle to larger projects, I think. So even here with this system, and I think I'm not telling you anything new here, and all the parts are unique. Each part has information about the positioning and the orientation embedded in the shape of or in the form of a code. Everything is there was like zero tolerance. We're working towards like zero tolerance. Everything either fits or it doesn't. So it's like, that's the thing with these puzzles. It's they either fit or they completely don't fit. Also, if one part breaks, you can't produce any spare parts, because you would have to decide which of the 2,000 unique parts you want to produce twice. So, yeah, like luckily, like none of the parts were missing, none of the parts broke, but. Yeah, that's the problem with these kinds of puzzles. So now, in 2016, I went back to Munich, and I always wanted to do my own thing, and I always wanted to have like a product-based, like a secondary venture, and. At the time, I was experimenting with shapes that I was posting on the Grasshopper forum, and like a random jeweler from Florida approached me, if we wanted to make like a collection together, and I said yes, of course, yeah, let's do it. And then I never heard back again. So my partner and I, we just decided, okay, let's see if we can print these things. We ended up printing them, and. You know, like, and then also we noticed that people were interested in what we were printing there, and we ended up starting like a label for jewelry called Sian. We're still doing that. Although this is like that has the lowest priority, I must admit, of the three things that I'm doing. so yeah, we're focusing on just on geometries that can't be made with traditional craftsmanship. So we want to be outside of the competition of traditional jewelers. We only ever use like one material, which is gold, basically 18 karat gold, to celebrate the shape, right? So because the process of making these pieces is already like very time and cost intensive, the only like it wouldn't make sense to use a cheap material for it. So, well, on a side note, and also on a side note, why am I mentioning this? Because now the lines start becoming really blurry. So this is, of course, we're still doing DFMA because we're doing the whole thing. We know how they get produced, and we're in the role of designer, but actually we're also in the role of the manufacturer, and we need to sell these things. And the type is a product. It's not configurable. We thought about making it configurable, but then in the end, people like we noticed they don't like to have too many choices, and they're always unsure how to configure things. So we ended up not making them configurable. And also one other thing that I would like to mention is that it's very tempting for architects to start product-based businesses. Actually, I saw like many of my friends started one and then they stopped because they underestimate everything that is not design related, which makes for, after a while, makes for 80%. You have to, like business development and marketing sales, you have to find people who are interested in that. It's like, so if I had known, maybe I wouldn't have done it, so, so to say. And also, what I wanted to mention is that when I talk to people and tell them, well, I do work on facades and I do work on jewelry, where they look at me and say, well, how they have nothing to, why are you doing such different things? But to me, it is still the same thing. It's, of course, it's like different materials, different typology, different scale, other like different material constraints. But at the core, it's still designing parametric systems consisting of rules and dependencies, taking into consideration material constraints to create, like in this case, aesthetic objects. All right, so. Still in 2016, after coming back from Sydney, I was given the opportunity to work on interior project, a club for electronic music in the heart of Munich. What you see here is it's the Deutsches Museum, the German Museum of Science and Technology. It's worldwide the largest of its kind. And here, this part, it's the Congress Hall. And here here there was a club for electronic music was meant to be made. So we were approached by the owners, like the people who would run the club, to design it. And the first thing they did was they bought this sound system here, which I don't know. I think the contrast isn't very good, but like what you see here is like a huge sound system, which was the first thing they had. It's usually used for outdoor concerts with 5,000 people, and so they wanted to use it for the club with 400 people. So it's like kind of over the top. And the room acoustician that was involved with the project told us, well, guys, you basically have to activate acoustically every bit of walls and ceilings. So we were looking for products that we wanted to use, like acoustic products, but couldn't find any that we wanted to work with. So we kind of developed our own surface system to absorb and scatter sound. So we came up with this concept of, well, let's call it bays that were inserted into the existing grid of columns, and all of these bays have rotated and tilted surfaces to avoid flutter echoes between parallel standing walls. So with this kind of club, you always want to aim for like a reverberation time of 0.8 seconds. The reverberation time is like a measure for how long it takes until the sound drops by 60 decibel, I think. So, and it's a good idea to avoid parallel walls. And then also these main tilted walls are made from 160 millimeters thick beech plywood, basically CNC-milled, so to additionally scatter the sound in the room. And then there is a second room, well, which you see here, and we developed an algorithm which places around 10,000 valleys over a wall of 20 meters in length, spanning over 3 different wall segments, and the pattern is, it works like a magnetic field. It follows, no, sorry, what was I about to say? Well, yeah, the pattern is non-repetitive over the entire surface. So we combined like a perforation and the material thickness, the relief made for like a good reverberation time in that room too. And so yeah, there's another image of that room. It's and so for these panels, we were working on the CNC milling path itself, which was what we handed over to the carpenter in the end. And it's kind of efficient. It was kind of efficient to produce these wall panels as the ball cutter that you see here. It's a different material here, but this the end effector is responsible to create the finished surface, as opposed to go like this, and well, it takes a lot more time. So after that project, we found ourselves applying that same algorithm to another project, where we were approached by an architect who wanted to do this for the ceiling. So we adapted that algorithm, and it's a different material, but we provided like CNC-milled panels for the ceiling of this house in Austria. And that kind of marked the beginning of the second venture. We started another, well, business, so to say, called Formfelder, like form and field, and which is really dedicated to developing parametric surfaces that are like have acoustic properties, are always unique, never like always non-repetitive over infinitely large surfaces, mostly made from solid timber, but also from other materials. So I'm just flicking through these images. Here the lines are blurry even more, I would say. Of course, still DFMA. We're still in the role of designer and the manufacturer, because we're actually like we make them in discrete formats and materials and perforation options, and they have a price tag. So that's like the project side of it. But then, of course, we're also what we like most is work on these individual projects where we take our own existing algorithms or develop new ones and apply it to different objects, walls, whatever. And then it's like even not clear, is this now a product or is it a project, and is it configurable or not? It is configurable for us, but not for the user. So it's kind of a mix of everything. So so there is one topic that sticks with us, and I want to show you one project here for a company called Blickfeld. They are a company based in Munich. They do LiDAR scanners for the automotive industry, and they approached us if we could do their booth for the CES in Las Vegas, like the trade show for customer electronics. And we took that principle of the LiDAR and applied it to the wall itself. The wall is made from folded strips from alucobond, like a composite material, and each strip gets folded 3 times, and the main faces of each strip are facing a certain point along a path, like the path of where the visitors would move along the long edge of the booth. So the visitor would see themselves in a certain movement pattern in those mirrored faces. I think there's like an animation where you can see like red, where we simulated this, like there's a red head and you see yourself in a certain pattern. So, and then coming from the left-hand side, you see yourself at one point in basically all the mirrors. So each strip has like a V groove and gets folded 3 times, and each strip has, of course, like slightly different folding angles. And then it's a system, because they were on a very tight budget. We had it produced in Germany. It got like flat packed and shipped to the US, and the team of Blickfeld could assemble it themselves, which was very important, because then they could save a lot of money by just installing it by themselves. And the system again was like it has those 4 faces, and on the outer 2 faces there are holes in the strips, and they align with the back wall, so the folding angle finds itself, so to say. So there was that project, and we did another project for the headquarters of Adidas in Herzogenaurach. And it's basically a room divider made from solid, or like from beech plywood again. And they asked us to integrate their logo, like basically when the design was finished, and the logo consists of 3 stripes, and it doesn't go well together with the organic pattern that we proposed. So we were looking for a way of integrating it in a subtle way, and we opted for like a perforation, like a backlit perforation. And because of the material thickness, that logo then only becomes visible when you're standing in front of it, in the front of the wall, and when you're at an angle towards the wall, you can't see it anymore. So to us, that was like a subtle way of implementing this. And so the overarching topic for these projects that I'm showing you right now is the activation of the position of the user, which to me, I find it very interesting. This is another project for that we just finished for a museum in Munich. Or maybe I just explain first. It's the Sudetendeutsche Museum. It's the Sudeten Germans are a minority, a German-speaking minority that had to emigrate from well, now Czech Republic to basically all across Western Europe after Second World War. And we took that migration map, and we wanted to visualize this this movement pattern. So what you see here is like a screenshot in Rhino. So again, we perforated this wall, but not in like with perpendicular holes in regards to the reference surface, but with inclined holes that are all oriented toward a specific, like to a movement path in the room. So from each position in the room, you would only see a certain set of light dots, and when you move through the room, you get this. Well, you get the movement. So it's very poor quality, I think, because it's so dark in that room. But you can see it on the right-hand side when you're moving through the room that the light dots move. And it's kind of in the eye of the viewer. They have to discover it by moving through the room. And last one, we're taking that principle. This is just a study. There's what you see on the left-hand side is just it's a rendering. We took that principle of using the position of the viewer and applied it to like a continuous surface, where all the individual faces are oriented towards the bisector between the viewer's location and a dedicated light source in the room. And that way you can activate each phase as like a pixel that reflects that light. So it's, maybe I'm not like, sounds very complicated, but when I juxtapose like four different, it's still loading. When juxtaposing 4 different geometric configurations of that same disk, you get very different movement patterns of light reflections. So it's just, this is an experiment, hasn't been realized, only works with very controlled conditions, meaning in a dark room with only one light source. So it's, yeah. So that's about, that about wraps it up for Formfeld. And I warned you, it's kind of complicated, but it's also like a journey which is not very straight. Like it led me to very different types of projects and things to do. The next 3 projects fall into the design to production, but in the role of the manufacturer or for the manufacturer. And this is like a configurable product. I think most of the time when we do, when we develop a grasshopper definition, well, at least for me, I'm the only one using it, basically. And then it's even sometimes when I do the grasshopper definition, I get the input parameters right, kind of, and I don't really change it later. So it's like this all parametric definition, which is at the same time a little bit dead because it's not being used, right? So to me, it makes a lot of sense for us as parametric designers or computational designers to work on configurable things, to work on configurable products, or even all the better, configurable buildings, right? So this was a project that we did for a supplier of medical orthotics. They do hand braces, which are there for correcting like a misaligned finger, for example, or to fixate a finger after an injury. And so we had to develop an algorithm that would produce a 3D model that can be printed based on the 3D scan of a patient's arm and based on the input of the doctor to speed up the process of manufacturing these hand ortheses or hand braces. The next one is it's a little bit of a different one, but it's also a configurable product. So we developed a web-based configurator using Grasshopper and Shapediver for a manufacturer of trailer tarpaulins. So admittedly, the product is not very fancy, but then sometimes we can, or this is my experience, I can get a lot of, like, there are always aspects that are interesting in a project, and it doesn't have to be the project itself or the object itself. In this case, it was clearly the task to make a configurator that was easy to use and is, well, you know, is aesthetic and easy to use. So this configurator outputs has a 3D view, but at the same time outputs like the cutting patterns for the tarpaulins. So it's kind of it's meant to be used by the manufacturer actually. Like that part and that part is meant to be used by the manufacturer, and that's the configuration part, which is the one that the end user would use. And then a third project, which is which we are actually still currently are working on, is in collaboration with the Fraunhofer Institute, which you might know as the inventors of the MP3 file format. They approached us with this project. It's about encasements for statues over the winter to conserve them by keeping the stone dry. And keeping the stone dry means that you prevent the growth of moss over the winter. So they have developed this technology where they would use like transparent ETFE membranes to encase the statue, have like an air intake at the inlet at the bottom and the air outlet at the top that would create like a constant stream of air using the chimney effect when the sun is shining, of course, not when it's not shining. So and then of course we came up with like a family of shapes which resemble like a crystalline shape, and that outputs, of course, all the fabrication data, and like that could adapt to different shapes of statues and would output all fabrication data. So that's also then a configurable product working with the head of the manufacturer in this case. So to make it even more complicated, I've been working on projects since 2016 under the name VCD, Vorhammer Computational Design. But in 2019, I teamed up with a structural engineer, Dr. Matthias Beckh, who's also a professor at University of Dresden in the northern Germany. And together our aim is to work on projects where architecture and structural engineering and computational design converge, where there is no clear separation between the disciplines. So one project we were working on was in collaboration with the climate engineers from Transolar for 2 sites in Abu Dhabi, and it's called like climate intervention pilots, meaning it's like structures to establish a cooler microclimate in the hot, in the summer, in the public spaces of Abu Dhabi. So unfortunately, this didn't get built. I think it's due to Corona. We're still hopeful that they're going to build it, but yeah, let's see. So this is like a structure with a retractable shading system at the top. This is very important because during the day you want to provide shading, and at night you want to retract them and give exposure to the cool night sky to let the ground cool off. And then there's also greenery underneath and a system that would provide like dry mist, and the combination of all this would generate like a cool microclimate underneath. So this was the first this was one side, and for the other side we developed like a system of rigid, like umbrellas with rigid petals, timber clad, that could also fold up and down, and by folding up it would expose the ground underneath to the cool night sky. So maybe I have to hurry up, I think, right? Okay. So another project where we just contributed like one little part was this competition entry by the architects Schulz and Schulz, based in Berlin. And here we just contributed like the facade system based on the analysis of the occurring forces in a reference surface. And that's a project that we are currently working on. This is actually the largest project we're currently working on. It's the extension of the parliament in North Rhine-Westphalia in Düsseldorf. It's those 4 cylindric buildings, and so we're officially in the role of the structural engineers here. But my part, or my team's part, is handling the the digital model. It's a BIM project, but also then here there is an area where the design and the architecture and structural design converge, which is the undersides of these 4 cylinders made from in situ concrete. And we developed so the architect said, okay, guys, do you want to develop something and think about something? And we developed like a organic shaped rib system that would follow the flow of forces. And okay, so this is another project that's also another large project we're currently working on, which is much it's progressing much faster than the last one, because the last one is set to be, like, completion is set to be in 2032. So we've just completed stage 3 with the last one, but this one we just completed stage 5. It's a fabrication hall for a manufacturer of industrial kitchens based near Munich, and so here there is no design involved. So my part, or my team's part, with like 3 people working on it, is just modeling for BIM, doing everything in Rhino, doing all the documentation, and that ties into that 4th point that I was mentioning at the beginning. Here, my core interest is improving the workflow, right? Because it's like coming up with even folder structures, conventions of naming Grasshopper files, developing little tools that everyone knows and everyone in the team knows how to use, and that's also a big challenge. And well, it gives me a lot of joy, like improving this from project to project. So this is a very dry thing to do, but for example here, again, we automated the production of these detailed drawings, like all the key details, and along the way it's good to learn about construction. So the last project that I want to show you is this pavilion, which you might have seen. I was doing that while teaching at the University of Biberach in 23. I was holding adjunct professorship for 2.5 years. It's a pavilion made from birch plywood, 9mm thick. I'm gonna show you a movie. Yeah, the sound is disabled, but doesn't matter. So here I try to show them the same principles that we applied at ARMA, like creating a system that would discretize an arbitrary freeform surface into like flat parts which are torsion free, and with small parts that can be assembled by a team of students. And so as opposed to the one in Sydney would have cost like, I think, $500,000 Australian dollars had we not been had the material and machine time not been sponsored. So, but this is like, the aim was to create something that can be made from cheap material, but also that could be fabricated by a normal laser cutter that you find in basically every carpentry, right? So I'm gonna talk a little bit about the build-up. We have, everything is based on, like, as I said, it's like it can be applied to any arbitrary freeform surface. There's just more favorable or less favorable shapes in terms of forces. So it's based on like a triangulated mesh. We did some optimization here because they have to be as equilateral as possible. That's important for the cells to work. And then there's an outer layer and an inner layer. That's the outer layer. That's the inner layer here. It's like star-shaped nodes. And then we have these. They don't touch, right? Because we have the laser cutter that can only do square cuts, so they can't be joined. And we have these connecting elements here with finger joints that would transfer the forces. And everything is held together by a central screw here, pushing everything together. And then also we have these C-shaped brackets that could be inserted into those slits here to prevent the ends of the star-shaped plates to be deformed. And we weren't sure if we needed them. We ended up using them along the perimeter of the pavilion, not everywhere. I would have wanted to only use those wooden C-shaped cleats, not the screw. But the structural engineer Jonas, who was involved, like said, okay, no, he's not comfortable with it, like, because it would have been nice to have like timber only, a timber only system. Well, as of course it's a parametric system, and I want to talk a little bit about the rules for the inner layer and the outer layer. So the inner layer varies in width. So we integrated like a Karamba part in the grasshopper definition that would analyze the occurring forces, and no surprise, you get more compressive forces at the bottom near the bases than at the top. So the width of the legs of the stars are derived from the compression forces in the system. And the outer layer, the rule for the outer layer is it has to be as wide as the inner layer, but it can be wider, and even that wide that it forms like a closed hull at certain points. So we were just generating a couple of variants on this. I think we decided to go with this one, like being more closed at the top to provide shade, and then being open near the bases. Well, here you see all the parts nested onto flat sheets of birch plywood. Each part has a label, like each part is unique and has a unique identifier, but also then each part has the identifier of its neighbor engraved, so it knows like what way it needs to be connected to the last one. So maybe the last thing that's worthwhile mentioning is we considered a couple of different options how to assemble it. First we thought let's do it part by part, starting from the basis and then meet at the top. And the second option would have been, it's actually what the manufacturer suggested, who let us use their machines. He said, well, start at the top patch, and then work your way towards the basis. But that wasn't possible because we would have needed a crane, obviously, to lift it up and keep it suspended, or build it upside down and then flip it. But then for flipping it, we would have needed a crane again. And the third option was to pre-assemble those segments, like split it up into segments, pre-assemble them, and then put them together. That we noticed wasn't possible either, because it's actually very tricky to join two pre-assembled segments, which then has many points where all the parts need to connect at the same time. And that would require to keep it in perfect position while you put the star nodes. So we ended up with a mix. We pre-assembled the three bottom parts, like A, B, and C, and from there on we worked part by part towards completing the first arch, and then when the first arch was completed, working towards the other end. And yeah, so I think this that about wraps it up. Thank you very much. Happy to take questions.
Oh, thank you so much, Simon. I think that it was like impressive. You know that in this program, in this Master of Parametric Design in Architecture, we try to drive this holistic approach, so that we as architects, also like here in Spain, we tackle like several things, from landscape design to urban planning to the smaller details of like construction and architecture. And I think that I'm glad to see that you also, like with like these tools from computational design, you have like also deal with all these at all these like different scales. No? I don't know if there are like some questions from you guys. Yeah, Arvin.
I saw your speed detail in the previous project.
Yep.
You said you had automized the junctions.
Oh, sorry. No, we didn't automate the entire thing. So we automated one part there was deriving, like we ended up modeling like chunks of details, and we automated the process of generating the drawings from it, but then again we could not automate the annotation part. So it's like just automated one part.
The modeling was done in Grasshopper, the junctions?
Yeah. Well, like all the projects are entirely made in Rhino and Grasshopper, like nothing else.
I think that this is like linked with something that we do at the office also, which is that we just want to submit files straight to the manufacturer.
Yeah.
You know, like the AutoCAD file for laser cutting or something like this. And at the end, in some project, it is like mandatory to submit these like shop drawings with these dimensions that probably nobody will use because everything will be laser cut. And I don't know, it's like just like somehow like a waste of time, but it's like mandatory. And we have been like discussing this a lot also in the office, like how can we like Rhino inside Revit, how can we like automate all this like painful process, you know?
I mean, yeah, well, on one hand, it's also a question of responsibility, right? Because for the Sydney project, we were working for the contractor, and we were generating fabrication data that went straight to the machines. But contractually, we were not responsible for it. Because this is like, it's crazy then, because if one thing is wrong, the office would have been ruined. So we were working as consultants, and it was their duty to check in the end before it went into production. So that was like the part where we actually ended up having to produce plans, or at least something that they could spot check, right? And the other thing is, like my colleague Jonas has put it nicely last time, like by producing all these drawings, it's not completely senseless, because we're kind of practicing the building, like we're getting to know it by taking sections and displaying it and producing plans. It's not, I do get it why it is important to produce plans after all and not work entirely from the 3D model, but it's so like, yeah, it takes a lot of time. Or maybe just the tools for viewing a 3D models aren't good enough or commonly used. Like most of the other people we're working with are not good at viewing 3D models. Maybe that's the thing.
Is there like any other question? Yeah, Joseph.
Sorry, I didn't get.
Which printing technology were you using for the 3D printed jewelry projects? SLA or?
So it's the print. It's based on a wax print. So SLA. Yeah. So it's a lost wax casting process. Yeah.
Yeah, Bruno.
Simon, you have developed several projects in different fields. Did you ever face the need of using like more complex programming tools than Grasshopper, for example, Python, C#?
Yeah, I know a little bit of Python and C#, but I'm by far not very advanced with it. Well, you asked me this earlier, like, did you do all the programming of the web-based configurator? The answer is no. There's a guy who cared for the interface, and it's the same for the more complex tools. So we have one guy, he's called Romuald. He's very advanced with C# in Rhino, so if we need like tools, then he's the guy. So I consider myself a little bit of not an expert in either like programming or construction, but my expertise lies in knowing a bit of everything, basically, and connecting the dots. If you say you can't know everything, but most of the time, I mean, it's very often that there is a plugin already that solves what you need to solve. So yeah.
I think I agree. Like when you focus on the design side, it's like you have to be aware of the amount of time that you spend to build your own tools? Like if sometimes it is like mandatory because you are, I don't know, working on something that requires some recursivity or something like that, and you just like end up using Anemone, or you program your stuff with Python.
Yep.
But most of the times, if there is a plugin, just use it, solve it, and go to the next step, right?
I think the case where I need to use Python most is when I have to loop through something, and I don't want to do it with Anemone because it's kind of clunky. So that for loops I use Python. That's
yeah.
I don't have like a question, but I have like more of a reflection.
So in the Carpax project, you can say it's a low tech. It's not low tech, but it's a low tech in a manufacturing side, but it's a high tech on the design side.
Yeah.
So I would say that sometimes like our projects get this complexity that actually demands this complexity from the manufacturer too. So that so there is like a certain, let's say, level where like a sweet spot where you can do complex stuff without complexity in the manufacturing process and without like reducing your manufacturer options to like 2 or 3 guys who actually can understand or maybe just deal, I don't know, with 3D parts.
Yep.
For example, with the Korean project and that stuff, right?
Yeah.
Like it's finding for the project the right spot on how high tech or low tech will be the manufacturing process, right?
Yeah. I mean, for most of the projects I was involved with, in the end, it wasn't that complicated, the manufacturing process. It always comes down to cutting stuff from planar elements in the end. Maybe I'm not doing the really complex stuff, so that's maybe a different thing. But for me, at least, the complexity always lies in the design part. Yeah.
Yeah. Just like a brief question, like that I had from some time ago, like in the Trifolium Pavilion, you were using different molds for the Korean boards on the outside.
Yeah, well there are.
But like a lot of different molds, or you did like an optimization there, like to use a limited amount.
Like all the doubly curved elements had their unique molds.
Okay.
And all the single, and there was like 2 different molds for the singly curved ones, like with 2 radiuses. But
for the stainless steel parts on the
no,
inside.
the stainless steel parts were bent in place, like they were just But I mean for the
for the shape on the outside, you were like clustering parts which were single curvature.
Exactly.
And there you were using a couple of molds and then doubly curvature.
So basically all these parts here are singly curved. Like up to here, it's 1 radius, so we could use the same mold. Up here, there's like a smaller radius, which made it necessary to use another mold. And then, like all the transition parts, which are doubly curved, had their own molds. So it's you could argue that this is like we were fabricating a lot of waste to manufacture this, and this is also why I said like I like the projects, but I think it's kind of over the top. I prefer working on stuff that is more easy to make and doesn't produce any waste along the way.
The result is impressive, so I think that it's worth to do. It was worth to do this.
Yeah.
One last question? No? Then thank you very much, Simon.
Thank you.